Okay, hi guys. So in my last video I talked about how the fundamental theorem of calculus relates to the concept of displacement. And in this video I'm going to give some examples to kind of back this up, and I'm also going to talk about how the fundamental theorem relates to the concept of total distance traveled. So as we remember, the fundamental theorem is basically saying that the integral of f of x from a to b dx equals uppercase f of b minus uppercase f of a, where uppercase f is an antiderivative for f, and therefore that means that lowercase f is the derivative of uppercase f. So what we kind of saw here is that if we have the derivative of a function, which we have here, lowercase f is the derivative of uppercase f, we can use that derivative to calculate the change of the function, which we see here by taking the integral of lowercase f of x, which is the derivative of f, from a to b. We can calculate the change in f, uppercase, from a to b. So with displacement, we are doing something pretty much the exact same, but with particle motion. So as we saw, displacement is the change in position, aka x of t1 minus x of t0. And we saw that displacement equals the integral of velocity from time 0 to time 1 dt. So we can kind of set this up. Since we know displacement is the change in position, we know that displacement equals this, we can set these two things equal to each other, and this looks awfully similar to the fundamental theorem of calculus. We are using the derivative of position, which is velocity, to calculate the change in position, which happens to be displacement. So that is why this formula works. So now let's give an example for this. So let's say I walk to my kitchen from my room, but then I realize I left my phone in my room. So I walk back to my room and I get my phone, and then I walk back to my kitchen. And remember, all the motion we're studying is one-dimensional in the first semester of this calculus course. So what is the displacement here? So let's say my room is 5 meters away from the kitchen. I start in my room, I walk to the kitchen, realize I forgot my phone, walk back to my room, get my phone, and then walk back to the kitchen. So as we see, our starting point is here in my room, and my ending point is here in the kitchen. So what is the displacement? What is my change in position? It is simply just 5 meters. We are 5 meters away from where we started. It doesn't matter about what happened in between. We're just looking at start and ending, and the change in that is just 5 meters. So now let's look at the graphs of position and velocity and implement what we learned here and see if the displacement is still 5 meters. So the position graph. So remember, in this scenario, we're starting in my room at 0 meters. We're walking 5 meters to the kitchen, seeing that we forgot my phone, walking back to my room, getting my phone, and then simply walking back to the kitchen. So the velocity graph for this, since we are moving 5 meters in 3 seconds, we're moving at 5/3 meters per second. So velocity is 5/3 meters per second for the first 3 seconds. Then it's 0 meters per second because we're at rest for a second. Then we walk back to my room at negative 5/3 meter per second. Then we get my phone, and then we walk back to the kitchen at 5/3 meters per second. So let's implement what we learned up above. So we said that the integral of velocity from a certain time to a certain time equals displacement. So let's see. So from 0 to 11, the integral of velocity, we just calculate the area under the curve. 5, -5, and 5. And if we add all those up, we get 5. So the displacement is 5, which we predicted here. So as we can see, this formula, displacement equals the integral of velocity from time 0 to time 1, that makes sense because of what we learned in the fundamental theorem. Velocity is a derivative of position. So therefore, we are using the fundamental theorem to calculate this change in position, which is displacement. Okay, so now I want to talk about how the concept of total distance traveled relates to the fundamental theorem. So as you guys learned from Mr. Huff's video, total distance traveled is just how far you've gone. It's like the odometer on your car. It's just adding up all the distances whether you are reversing with your car or going forward in your car, and that is your total distance traveled, or the number that shows up on your odometer. So total distance traveled is really the change in distance. And distance is the antiderivative of speed, and speed is the absolute value of velocity. So therefore, speed is the derivative of distance. And as we see with the fundamental theorem of calculus, you can use the derivative of a function to calculate the change of the function. So that's exactly what we're going to do here. We are going to take the integral of velocity from a to b, and this will give us a change in distance, which is total distance traveled. So this is exactly how you calculate total distance traveled. So in essence, what we are doing is we are using the derivative of distance, which is speed, to calculate the change in distance, which is total distance traveled. So now I'll give y'all an example for this. So let's say I walk to my kitchen, I grab a snack, and then I walk right back to my room, and I started in my room. So I start in my room, I walk 5 meters to the kitchen, grab a snack, and then walk back. So while our displacement would be 0 because we end up right back where we started, so there's no change in position, our total distance traveled is really just adding up all the distances we go. We go 5 meters, and then we go 5 meters back. So our total distance is simply 10 meters. So let's look at the graphs for this. So position, we are moving 5 meters as we travel from my room to the kitchen in 3 seconds. Then we take a 4-second break to grab a snack. And then I walk back at the same speed back to my room. So now let's look at how this would look in the distance traveled graph. So we are moving 3 meters to go, we are moving 5 meters in 3 seconds to go to the kitchen. We are taking a break, and then we are walking back to my room. While position shows this walking back to my room as being negative, distance traveled is just continuing to add that as more meters traveled, and that is the difference with distance traveled and position. So now let's look at the speed graph. So speed, as we can see here, we are traveling 5 meters in 3 seconds as we go from my room to the kitchen. So our speed is 5/3 meters per second. So we're traveling at 5/3 meters per second for 3 seconds. Then we take a break to grab a snack, so my speed is 0. And then we walk back at the same speed at 5/3 meters per second. So now let's calculate what the total distance traveled is by using the integral of speed. So the integral from 0 to 10 of absolute value of velocity, which is speed, is just calculating all the areas under the curve. So 5 and 5 equals 10, which is what we predicted this would be. We predicted this whole distance would be 10. And this is really just showing us the difference between speed and velocity. In the last problem, where I forgot my phone in my room, the velocity was negative when I walked back to my room. Well, here the speed is positive because there cannot be a negative speed. So that is why speed and total distance traveled relate so well. So really what we have done here is we are simply just using the derivative of distance, which is speed, to calculate the change in distance, which is total distance traveled, using the fundamental theorem of calculus.